Good morning, good afternoon, or good evening, depending on where you're sitting in the world and what time of day you're tuning in. My name is David Mays, and I'm a professor of civil engineering in the Department of Civil Engineering at the University of Colorado, Denver, here in beautiful Denver, Colorado, USA. Within my department, I'm involved in the graduate track in hydrologic, environmental, and sustainability engineering. And one of the common themes that ties together those subdisciplines within civil engineering is the study of fluid mechanics. Fluid mechanics includes the movement of gases and liquids. And we certainly don't own that here in civil engineering. But one thing we do in civil engineering is provide water to people, and then we collect the wastewater for treatment. We also do a lot of work in environmental cleanup. So understanding fluid mechanics is pretty important if you want to keep populations healthy and vibrant, and if you want to protect environmental quality. So here we're going to think about one of the basic components of fluid mechanics. There's fluid dynamics, where things are moving, and then there's fluid statics, where the fluid is not moving at all. And what we're going to focus on today is going to be hydrostatics. If you've ever been swimming in the sea or in a swimming pool, you'll know that the deeper you go, the more pressure you feel on your poor ears. Your eardrums are not designed to resist that much pressure, and it hurts. In this diagram, we can see that at the water surface, we have about 1 bar of atmospheric pressure. All of the air between us and outer space, when you add it up, it's 1 bar of pressure. If you swim down 10 meters, which is about 30 feet for those of you using US units, that is as much pressure as you have from the entire stack of atmosphere up above, because water is much denser than air. Every time you go down another 10 meters, you get another bar of pressure, and it adds up in a hurry. In fact, one of the hazards of scuba diving is that as we pressurize our bodies, gases in our blood go into solution. If we come back up to the surface too fast, some of those gases can turn back into bubbles that are not dissolved in the blood anymore, and this causes what's called the bends. But beyond this particular hazard for scuba divers, there's some really cool stuff we can do with hydrostatics. And to get going on this, I want to present 2 basic definitions. The first one is the definition of the fluid density, symbolized by the Greek letter rho, which is just going to be the mass per volume. The more mass you have in a given volume, in a liter or a cubic meter or a cubic foot, the more density you have. And liquids have much more density than gases almost all the time. The second definition I want to present is that of the pressure. Pressure is symbolized by a Latin capital letter P, and it's going to be the force divided by area. So instead of thinking about forces, we're going to be thinking about pressures. Figure 3 illustrates the force, which is a vector. It has a magnitude and a direction, and the perpendicular area, capital A. Because we're always thinking about perpendicular areas, we're mostly going to think about force for the rest of this presentation as a scalar, because it's just perpendicular to our cross-sectional area. Once we have this definition, and we have the definition of density, this leads us to the big equation of hydrostatics, which is that pressure is going to be rho times g times h, where h is the distance from your free surface down to the place where you're calculating your pressure. This figure shows the cross-sectional area inside a beaker, but it also shows the difference from the water surface down to that point. And that is the one thing that matters. The deeper you go, the more hydrostatic pressure you're going to feel. So let's talk about this a little bit, because this leads to some possibly paradoxical results. Figure 5 has 3 sections. In the top section, we're imagining a large swimming pool with rectangular sides full of water. Nothing unusual about that. Then, on top of this water, we're going to draw some dashed lines. Those dashed lines don't mean anything yet. So when we draw the dashed lines, it's not going to change the pressure distribution. But now, in the second panel, let's think about what happens if we replace those dashed lines with solid lines instead. Well, we haven't moved any fluid, And each one of these shapes is still open to the atmosphere. So we haven't changed any of the depths. So we still haven't changed any of the fluid pressures. So now let's go down to the third column, where we're going to imagine draining the swimming pool, except for the water that's been trapped inside our shape with all the jagged edges. Well, we haven't changed any of those fluids, so we haven't changed any pressures. And this leads to our first result. It takes a little bit of getting used to. The pressure at the bottom of each one of these, whether it's a tube or a wedge or a zigzag, is always the same. It doesn't matter how much water is up above. It doesn't matter the shape. The only thing that matters is the depth. This also leads to something that we call the hydrostatic paradox. This is an illustration of what we call the hydrostatic paradox. What we have here is a large sack of fluid, and it's supporting a heavy weight, capital W. And the way we're doing that is by connecting this to a tube. It's a small tube, but the tube has a lot of height. So even though the weight of fluid in that small tube, a small letter W for the weight and small a for the cross-sectional area, not that much weight. But what we have is enough pressure to spread it over a larger area. And that larger area is enough to support the large weight. So again, the key thing that matters here is depth. The shape doesn't really matter. All that matters is how deep we are. And this allows us to come up with some pretty useful hydraulic levers. Figure 7 is an illustration of a hydrostatic lever. On the left-hand side, we have a small force applied over a small area. On the right-hand side, we have a large force applied over a large area. And the reason those two go up and down together is because the pressure underneath is the same. And the pressure is always a force divided by an area. So this gives us a way to lift up heavy objects without having to apply a lot of force. Just like a regular lever, where you have a large translation with a small force times a small translation in a large force. Of course, there's no free lunch here. In order for that to work, you'd have to move the small column on the left much farther than you move the large column on the right. So it ends up working out to be the same. What I'm showing here is another way to think about the distribution of hydrostatic pressure. If we imagine a column with 3 holes in it, the hole at the top is going to be dribbling, the hole at the bottom is going to be shooting out as a jet, and the hole in the middle is going to be somewhere in between. And that's because the deeper we go, the more hydrostatic pressure we have. This distribution of hydrostatic pressure leads to some interesting applications. For example, if we're running a hydroelectric dam, we would want to put our generator as close as we can to the bottom. If it's close to the bottom, we're going to have an enormous amount of hydrostatic pressure, and that pressure is going to generate a lot of velocity, which is going to run the turbine really, really fast. That's going to generate a lot of electricity. And it's a pretty green form of electricity too. Very little carbon emissions are associated with hydropower. We'll get back to that at the end of the class when we take a look at Hoover Dam. But I also want to spend some time thinking about the distribution of pressure, because that helps us think about the equivalent forces that result. And that's pretty important if you're designing a hydraulic structure, because you have to make sure the structure is able to resist the hydrostatic loads. What I'm showing here is another cross-section through the side of a swimming pool with rectangular walls. The same thing that we looked at a couple of times earlier in the video. In this case, there's a flat surface on the top with an upside-down triangle. That is the standard symbol to say that liquid is open to the atmosphere. And it has a total depth of y. We know that the pressure is going to be rho times g times h, where h starts at the water surface and goes down. So at the top, there's no hydrostatic pressure. As we go down to the bottom, we get the maximum hydrostatic pressure. And in between, we'll have intermediate amounts of pressure. When we look at this triangle, we call that a pressure prism. It's the distribution of hydrostatic force. And if you've studied any material science and engineering, that would be an example of a distributed force. So if we go back to our second equation, pressure is force divided by area. We can rearrange that to say that the force is going to be a pressure times an area. And as long as we have a constant pressure, that works fine. But in this case, we don't have a constant pressure. What we have here is a pressure that starts at 0 and it goes down to a maximum. So what we're going to do instead is we're going to reframe that as the force is the average pressure times the perpendicular area. That average pressure is calculated at the average depth. The average depth is what we call h sub c, where the c means centroid. It's the depth from the water surface down to the centroid of the flat surface that we're analyzing. The reason we do a centroid is we don't always have rectangles. Sometimes we have triangles, sometimes we have circles. Any flat surface is going to have a centroid. So we can generalize by thinking about the centroid depth. Once we know that, the average pressure will be rho times g times h sub c. That's the average pressure. And then that gives us an equation to calculate the equivalent force resulting from the hydrostatic pressure. It's going to be rho times g times h sub c times the cross-sectional area, capital A. And that allows us to calculate some forces that we can use for designing structures. Here's an example that comes from an aquarium. If you've ever been to an aquarium, you've probably enjoyed looking at the sea life while also enjoying the abundant air that was available to you on the human side of the window, where you're not having to hold your breath and swim. So here's an example where we've got a window submerged by water. So in this case, the area is going to be 3 meters deep times 4 meters wide, giving us an area of 12 square meters. The h sub c is going to be halfway down to 3 meters. So that's going to be 1.5 meters. G, as always, is 9.8 meters per second squared. And then rho for water is going to be 1,000 kilograms per cubic meter. If it's a seawater aquarium, the water would be a little denser, 1,025 kilograms per cubic meter. And when you multiply all those three numbers together, that gives us a total force on the window. By the way, when we ran through this, we never made the assumption that the wall is vertical. That equation also works if you have a window on an angle. Here's the same kind of aquarium tank, but now the wall is at an angle. But we can still define the depth of the centroid of that surface and then the perpendicular area. So the same equation works whether we have vertical walls or walls on angles. Now let's shift gears a little bit and think about what happens if the surface is not flat. As long as we have a flat surface, all of the pressure components are going to be parallel. They're all pushing in the same direction, so we simply multiply the pressure by the cross-sectional area. As long as the pressure is constant, that'll work. But if we have a curved surface, then we're looking at a distribution of directions. And that complicates things a little bit because a pressure is always perpendicular to whatever surface it touches. If you have a curved surface, you'll have a distribution of directions, as shown here on the lower part of the cylinder. On the upper part of the half cylinder, it's flat, so all of those pressure components are the same. But if you can imagine submerging this shape into fluid, where the half cylinder is perpendicular to the water surface, there's not going to be any net hydrostatic force pushing. So the components pushing on the flat side are going to be equal to the components pushing on the curved side. And that gives us the answer on how to calculate curved surfaces. You take your curved surface and you project it into a vertical plane. What would this half cylinder look like if we projected it onto a screen? In that case, it would just look like a rectangle. And then we're back to analyzing the same kind of rectangular cross-sectional areas that we looked at a couple of slides ago. Here's an example of when that might be useful. Figure 13 is an aerial view of Hoover Dam, which is located on the Colorado River on the border between Arizona and Nevada in the southwestern United States. It's a concrete arch dam. It's called an arch not because it has the structure of an arch that we're familiar with from architecture resisting gravity. In this case, the arch is horizontal. And we make it horizontal because we're resisting a lot of hydrostatic loads. We have to take those forces and put them into the rock on the side of the canyon that can resist the loads. So here's a perfect example of when we would take a curved surface and have to calculate the equivalent hydrostatic forces. By the way, Hoover Dam is also a nice example of a hydroelectric power generation station. If you look at the bottom of the dam, you can see that they have an electrical generating facility, And that's always at the bottom of the dam where we have the maximum hydrostatic pressure. And again, that goes back to the third equation. The pressure is going to be rho times G times H. So where we have the maximum depth H, we're also going to have the maximum pressure. Let's take a look at this to help us think about one other cool dimension of hydrostatics. What I'm showing here is a box that has been submerged in our favorite swimming pool with rectangular sides. So here's the box. If you look on the left and the right, you can see that you've got a pressure prism on both sides. There's going to be some pressure at the top where the box is under a depth of H1 from the surface down to the top of the box. And as we go down from H1 to H2, the pressure increases. So we have a pressure distribution on the left and a pressure distribution on the right, but they cancel out exactly. That's not going to give us any net force on the box. However, when you look at the top of the box and the bottom of the box, it's a different story. On the top of the box, you've got a constant pressure of rho times G times H1, pushing straight down. On the bottom, you've got a constant pressure of rho times G times H2, pushing straight up. But the forces on the bottom are bigger than the forces on the top because depth matters. The deeper you go, the more hydrostatic pressure you have. And the net result of this is what we call buoyancy. Buoyancy is a force on an object submerged in a fluid that's equal to the weight of fluid that has been displaced. And that's called Archimedes' principle, going all the way back to ancient Greece. Let's take a look at how that might play out. This is an illustration of buoyancy forces on a ship. And it varies because the waves go up and down on the side of the ship. Near the bow of the ship and the stern of the ship, the waves are deeper. So there's more buoyant force pushing up. In the middle of the ship, there's relatively less. So there's less buoyancy force. And that has the effect of applying some bending forces to the ship. Resisting those forces is one of the major challenges in naval architecture. In the lower slide, we see the same ship going through a canal. And because the ship itself is displacing a lot of the water, it accelerates the fluid, which magnifies the waves, which also magnifies the changes in hydrostatic loads that the ship has to resist. So that brings us to the end of our quick introduction to hydrostatics. We defined the fluid density, we defined the pressure, and we got to the basic equation. Pressure is rho times G times H. Then we talked about how important the depth H is. We talked about how to calculate forces based on perpendicular areas. And then we talked about the effect of buoyancy, what makes things float. We do not have any ships like the one I just showed here in Colorado. But if you're interested in studying this aspect of engineering, you can do this at colleges anywhere in the world. If you're particularly interested in moving to Denver and experiencing what it feels like to live your life at Mile High, we would love to have you get involved with our program. Thank you very much for your interest and have a great day.